Good morning, good afternoon, good evening. My name is Stefano Marchidis, and I'm going to be the teacher and examiner of the course Quantum Computing for Computer Scientists. In this lecture, I want to give you a brief introduction to the course. I'm going to touch upon about requirements, materials, and how to pass this course. Before start, I want to give you a few words about myself. I work at KTH since 2011 and I'm an associate professor of high performance computing. My research area perfectly aligns with the topics of this course. I work on quantum computing and quantum machine learning, so I'm very excited to spend the next few months together with you and learning and discuss about quantum computing. Let's say a few words about quantum computing and how exciting it is to work on it. So this course is really about learning about a leading edge of new technology, that is quantum computing hardware, but also software, a new science, how to design, implement algorithms, and also in a growing industry. So we will get to know all companies working on quantum computing hardware, but also software. So this course is designed for a computer scientist, but also we will have a chance to learn just enough about these exciting new technologies and also a little bit about quantum physics and how we can leverage quantum physics to do quantum computation. There is a lot of excitement about quantum computing. Some people say that is hype, right? It is not to stand. So there is also a little bit of naivety on what quantum computing can do today. So this course is also a mean for you to understand what quantum computing is today with all his limitation. I think one of the most important part of this course is really a way for challenging yourself to think about computation in a totally different way you are used to. For instance, we are going to start thinking about computation in terms of superposition, entanglement. And also we're going to start thinking what really quantum parallelism means. So there are many exciting concepts that are kind of disrupting, kind of new, so it will take some time for us to get it. It's challenging, but I can assure it's going to be highly rewarding. So why this course is called Quantum Computing for Computer Scientists? Well, the reason is that is focusing on concepts for computer science. In particular, the course is a programming first approach, and therefore we use for computer scientists. We focus on programming and practical aspects of quantum application. We will program in Python. We'll also execute the codes and our quantum codes on real quantum computer that today are accessible via the cloud. However, most of the runs will be run on quantum computer simulators running and executing on our classical computer. That is our laptop or our workstation. What are the intended learning outcomes of this course? After passing the course, you will be able to describe a complex number, a complex vector space for quantum computing. So we are going to look at all the math that you need to know in order to feel comfortable with quantum computing. You will also be able to describe what it means, superposition of states, non-locality effects like entanglement, and probabilistic laws that are at the base of quantum computing. You will be able to compare the advantages and disadvantages of classical data processing with quantum computing. You will be able to generalize the concepts of bit to the quantum bit, classical gates and register to all the quantum equivalent concepts such as qubit, quantum gates, and quantum register. You will be able to list, formulate, and describe key algorithms in quantum computing. And last but not least, you will be able to describe hardware that can analyze quantum calculation in order to design quantum algorithms and programs that can run on current and next generation quantum computers. What are the prerequisites of this course? Well, we need some basic knowledge of linear algebra. I will provide at the beginning of this course, a reflection on the parts that we need for being successful in this course. So for instance, I'm going to talk about complex number and their properties, Hermitian, unitary matrices, product, and so forth, so on. You also will need a basic knowledge of Python, and the reason for that we're going to use quantum programming language that mostly based on Python. During this course also we will do assignment using Python, and therefore Python is one of the requirements for this course. Let me say a few words about the structure of this course and modules. This course is organized in 5 modules. We will start with the introduction and description of the fundamentals about quantum computing. I will describe a little bit of a history. I will provide you a refresher about the math for quantum computing. I will give you an introduction to the concepts of a quantum state and how we can use quantum states for the qubit. And then I will provide you an overview of the technologies that we're using quantum computer and a high-level programming approach. The second module will be about how to formulate quantum application and quantum algorithm using quantum gates and circuits. In the third module, I'm going to talk about quantum programming primitives. What I will discuss quantum arithmetics, conditional logic, amplitude amplification, quantum Fourier transform that are the basic building blocks to build a larger quantum application. In the fourth module, I will discuss quantum application. I will talk about quantum search, short algorithms, encoding quantum state, and quantum simulation. In the last part of the course, I will discuss the final project, and you will perform the final project about quantum computing. A brief timeline of the course. In period 2, we will cover module 1 to module 4. In the period 2, we will focus on the final project on quantum computing. Period 2 will have a lighter workload with respect to period 1. I want to give you a brief overview of the course activities. So this is a blended format course. So I will alternate in-class lectures with a number of video lectures covering important concepts in quantum computing. So as a part of this course, we have online pre-recorded lectures like the one that I'm teaching now that are compulsory. So at the end of the module, I will ask you to confirm that you have been seeing all the video lectures of the module. So we are going to have 10 to 20 small video lectures, typically can range between 5 and 20 minutes long. Also, we'll have some in-person overview lecture to introduce the module or to discuss with you about the course in person. So these are not compulsory, but obviously highly recommended. In order to assess your learning, also we will have between 5 and 10 quizzes per module. So these are individual, so we will need to use this quiz to assess your learning. So I ask you to try to reach 100% of all the questions. You can repeat these quizzes until you get the 100%. We also have a programming assignment that will allow you to touch in practice what it means to program quantum algorithms. We will have one programming assignment per module, and this can be done in groups of 1, so individually, or in groups of 2 or 3 people. In this case, the grade will be just pass or fail. In the second period, we will focus on working on the final project. I will provide 3 topics you can choose from and just focus on the topic that you would like to know more about. The final project submission consists of a final report and in-class presentation. This can be done individually or in a group of 2 or 3 people. The final project determines the final grades of the course, that is grade 8 to F. The grading criteria will be later posted in Canvas at the beginning of period 2. As I said, we will do quite a lot of programming of quantum computers in this course. We will use Python for assessing quantum computers and their simulator. You can use Python on your local machine, laptop, workstation. Also, you can use the cloud. For instance, you can use Google Colab notebooks. There are 4 recommended textbooks. When it comes to the mathematics part, I recommend Quantum Computing for Computer Scientists, Application, and the more state-of-the-art of quantum computing. I recommend the Quantum Computing Applied Approach. By far, my favorite books about the programming computer is this one, Programming Quantum Computers, by O'Reilly. That's something I will get quite a lot of material, especially in the second and third module. And finally, another nice and extremely useful book is Learn Quantum Computing with the Python and Q#. So I have all the details on these slides, so if you want to check. And all these books are available in electronic format through the KTH library. So how do you interact with me? So there are several discussion pages posted on Canvas. My suggestion and recommendation is to post discussion topic and discussion page on Canvas, so I can see them, I can interact with you. If you have a problem, just post it there. Keep in mind that many other people taking the course might have a similar problem, so it might also be very useful for all the other students to hear about what we want to discuss. Also, we'll ask you to avoid direct email to myself, and the reason for that is that I receive several emails related to research, teaching, administration at KTH. So some of your emails might get lost in my mailbox. So that's one concern I have. So please use the Canvas discussion page so I can get back to you, or other students who knows the answer to your question can also reply online. So this is this last slides, and talk to you soon.